Step 1. Prepare the body for freezing. Okay, so you can't just throw someone into a vat of liquid nitrogen and hope they won't die. Our cells contain water molecules inside them, and when water freezes, it expands, so the volume of the cell will increase to the point that they actually burst and die. And if you're planning to deep freeze a human, this would turn the water in your body into tiny razor blades inside your organs. So first, we have to extract all the blood from the test subject and replace it with a cryoprotectant solution that will prevent most of the cells from bursting or getting damaged. In fact, cryoprotectants are also used when freezing sperm cells and egg cells for in vitro fertilization.
Fun fact!
The first human birth using frozen sperm cells was reported in 1953 by Dr. Jerome K. Our best current candidates for cryoprotectants are substances like glycerol-based solutions, which can transport oxygen while lowering freezing risks. Step 2. Lowering the body temperature. Once the body is protected from ice damage, we begin the descent into suspended animation. The ideal temperature is around minus 196 degrees Celsius, the boiling point of liquid nitrogen. This ceases any type of biological activity or degradation, seemingly stopping aging at a cellular level. Now comes one of the biggest dilemmas in the process. How fast should the body be cooled? In theory, if we lower the temperature too slowly, ice crystals will start to form, which could damage the body. So we should lower the temperature at an extremely fast rate. This is known as vitrification, a process by which liquids, instead of crystallizing, directly transform from a liquid state to a glass state. This is easy for a single cell like a sperm cell or egg cell, but humans have a large volume relative to their surface area. The trick is cooling fast enough to prevent ice formation, but not so fast that your cells literally can't handle the thermal shock. It's a delicate balance, like cooling a frozen pizza without burning the edges and leaving the middle raw. Some animals, like the wood frog, naturally enter a similar frozen state during winter and thaw out in spring without damage. Step 3. Long-term storage and space transport. Let's be honest, the most exciting use of cryogenics is being able to travel the vast distances of space, not in years, but in decades. So let's dive into this scenario. Most cryonics companies today store frozen bodies in liquid nitrogen tanks, which naturally stay cold as long as they're regularly topped up as the nitrogen evaporates. But in space, that would mean having to carry excessive amounts of liquid nitrogen, making it unfeasible. A possible solution could be to use the extremely cold temperatures of deep space for a passive cooling system that would circulate the evaporated liquid nitrogen through space to lower its temperature before entering the cryo chamber again. If we're going to be in space for decades, cosmic radiation can become a big problem, damaging DNA and killing cells. To prevent radiation damage, one option would be to bury the cryopods deep inside the spaceship, protected by lead or water as these block out most radiation. Another option would be to use magnetic shielding, where, similar to Earth's magnetosphere, the ship would generate a magnetic field to deflect radiation. This would save space and weight, but require large amounts of energy. Step 4. Waking up. The ultimate challenge. 400 years have passed and we're ready to unfreeze our test subjects. The hardest part of cryogenic sleep isn't freezing the body, it's bringing it back to life. One of the biggest risks in rewarming is thermal shock, where temperature gradients within the body lead to uneven warming, causing cracking and cell rupture. But researchers have experimented with magnetic nanoparticles that are injected in the tissue before freezing, a procedure currently used in cryopreserved organs. When exposed to an alternating magnetic field, these nanoparticles heat up uniformly, preventing thermal gradients during defrost. Then, the cryoprotectant concentration is reduced gradually to avoid osmotic imbalance, where cells either swell or shrink. Now, the most delicate system to revive is the brain. Unlike other organs, neurons are highly susceptible to the freezing process. But techniques such as deep brain stimulation with mild electrical impulses, like the ones used to treat Parkinson's disease, or neural stem cell injections could help strengthen and repopulate damaged regions.
Fun fact!
In 2023, scientists unfroze a nematode that had been trapped in Siberian permafrost for 46,000 years. And it just started moving again like it was taking a long nap. Final thoughts. How close are we? Right now, human cryopreservation is still theoretical, but we're making progress. There are several cryogenics companies that are already preserving bodies, but they rely on future technologies for the revival part. However, there is hope. In 2024, the startup Cradle managed to recover electrical activity in a cryopreserved and rewarmed slice of rodent neural tissue. Nevertheless, NASA is exploring a more near-term option, hibernation or torpor for astronauts. Similar to bears during winter, This state reduces the heartbeat and metabolism, which could help reduce water and food needs for trips within our solar system. But could decade-long cryogenic sleep become a reality in the next century? Maybe, but one thing's for sure. If we want to reach the distant stars, we'll have to figure it out.